I'm delighted to welcome our faculty for today, Madam Dr. Lalita Gowda, my teacher when I was at CFTRI. Ma'am is a retired chief scientist at CSIR CFTRI. She obtained a PhD in biochemistry from Baylor University, Texas, and has had postdoctoral training at the Department of Biochemistry, University of Cambridge. Her professional experience as a research scientist, structural biology of foods and analytical biochemistry and food safety, includes grassroots work, academic activities, consultation, and institutional leaderships over a period of peer-reviewed publications in journals of international repute. Her exceptionally strong analytical skills and extensive knowledge of food analysis makes her the go-to person for all standard settings that FSSAI, EIC, and the other regulatory bodies in our country work with. Ma'am is part of chair of numerous panels at all of these bodies, BIS, FSSAI, EIC, and post-retirement, her passion for achieving the highest standards for knowledge dissemination and teaching is expressed through her support to programs such as the one happening today. Ma'am, a very warm welcome. Lalita, ma'am.
Thank you. Yes, thank you, Shubha.
Good afternoon, ma'am.
Good afternoon, and good afternoon, everyone. So I will just start go into the topic straight away, and I just will share my screen. Okay. Is the screen visible?
Yes, ma'am. Not yet in slideshow.
Yeah, I'm just putting it in slideshow. Yeah, it's in slideshow now?
Yes, ma'am. Perfect.
Okay. What I'm going to do today in the time that has been allotted is describe to you the measurement of uncertainty and exactly how you would go about it doing in the lab. So initially what I would do is discuss some of the basic requirements for understanding and doing the measurement of uncertainty, which is the basic arithmetic mean, standard deviation, etc. I will define what are these uncertainties and normal distribution, coverage factor, etc., which you have been hearing about. So you need to understand these basic terms before we go into the actual process of doing the measurement of uncertainty. I will describe in detail what are the different types of uncertainties that we experience in food analysis, and most of my talk would be confined to the analytical techniques that we use in a food analysis laboratory. And then after I finish the PowerPoint, I will actually take you through these calculations through the Excel sheets, the Microsoft Excel sheets, what we use and how easy it is. Of course, if we had more time, I could go through several examples, but I can give you at least, depending on the time, 2 or 3 examples. So today's topic is the measurement of uncertainty. And okay, so what is measurement? All of you know that it is the process of obtaining a value of something. It could be the length of a scale, or it could be the weight of a person, mass of some food that you're eating, etc. That particular measurement or the quantity that we measure is called as the measurand. So I will be using this term measurand, or in common parlance, this is known as the analyte concentration, etc. So that the measurand as such is generally the concentration of the chemical entity, what we are measuring. And in case of food analysis, it could be moisture, it could be the defective grains, it could be the salt content, sugar content, etc. So the chemical entity that is intended to be determined, as I said, is called the analyte. So these are the examples: lead concentration in water, or the pesticide thiobendazole in an orange, or the protein content in a bottle of milk. Measurement, why do we do measurements? The most of the experiments we do, and to convince everyone about the thing, the scientists generally make a measurement. And if you look at the measurements, they are rarely the same. And they always differ. Whatever measurement you make, it differs a little bit from what is the true value. This deviation from the true value is what we term as error. So I want to emphasize that there is a difference between the measurement of uncertainty and error. So error is the deviation from the true value. Say I expect the scale is about 12 centimeters and I measure 12.1, then that 0.1 is the error. It is not the measurement of uncertainty. It is the error, the difference from the true value. So the aim of any measurement is to obtain the true value. But it is very difficult to get the true value, like to hit the nail on the head to obtain the true value. And what we generally get in an analysis or an analytical procedure is a value which is as close as possible to the true value. Our measurement result will just be an estimate of the true value, and the actual true value will be unknown to us, especially when we come to food analysis. So therefore, we cannot exactly know how near we are to it, and the measurements that we make almost always have some uncertainty associated with it. So the difference between the measured value and the true value is called the error. The errors can either have a positive sign or a negative sign. So you will find it says plus or minus. So that is the error. And errors, I will explain a thing as I go along in some of the later slides, can actually be regarded as two types of errors. One is the random error, and the other is the systematic error. The random error is something which changes. If I do an analysis and you do an analysis, it will be different. And that error is the random error. A systematic error is an error which you cannot make change that error because it is so strongly associated with the system. For example, if your oven, if you have set the oven at 100 degrees, however, it reads 105, then that 5 degrees is an error. And this is a systematic error which will be carried over to any analysis you do using that oven. And the only way we can rectify that error is to either calibrate the equipment, recalibrate the equipment, or check whether some sort of an electrical problem or an electronic problem is there. So it is systematic unless we have rectified it. Irrespective, it just continues along with along the line. It's also a pipette. If there is an error in the pipette because you have not stored the pipette at the correct temperature, they're generally calibrated at say 20 degrees, and if we have been storing them at 37 degrees, due to the heat of expansion, there might be some change. That is a systematic error. So the error, like the true value, also the error is not known to us, and it cannot be used in practice for characterizing the quality of our measurement unless it's in agreement with the true value. So dealing with errors, first of all, we need to identify the errors and the magnitude of those errors. So once we have identified those errors and the magnitude, we can at least use some sort of methods to reduce or mitigate those errors. So how do we do this? How do we mitigate these errors or check? Is one, as I said, in the instrument, see whether we can get better instruments, maybe instruments which have higher sensitivity, or see that their calibration is done regularly and get it, calibrated by a certified agency, those who are certified with 17,025, etc. And or we could change the experimental design and see that we do not, especially in analysis. If you see, if you're dealing with very small quantities, you are weighing in terms of micrograms or nanograms, your error is very high. However, if you carry out the same experiment with, say, 1 gram, you will find that your error is low. Similarly, in dilution, if you have to make a 1 in 1,000 dilution, and you take 1 microliter and dilute it to 1,000 microliters, you will find the error is very large. However, on the other hand, if you first do a 1:10 dilution and then do a 1:100 dilution and finally go to the 1 in 1,000 dilution, you will find that your errors have reduced. So this is how, by changing the experimental design, you can reduce your errors. And the third is to understand, and this is to collect a lot of data. For example, if you're doing, say, a metal analysis, maybe you could collect for the same sample, collect data from at least, 10 or 15 different laboratories, and then you will understand where your error has come from. But the bad news is, no matter how good you are, there will always be errors. And then the question comes is, how do we deal with these errors, that thing? And when we talk about precision and accuracy, these are limited by the instrumentation that we have and the data gathering techniques. Okay, so the other bad news is you must use statistics, and basically you need a little bit of mathematics, not the very high mathematics, but mathematics to know and remember the formula for different types of statistical calculations. So now coming to what is uncertainty measurement. This uncertainty measurement is related to, and it tells us about the quality of the data. This uncertainty, as we talk about, is a doubt, as the dictionary, Webster's dictionary meaning says, uncertainty is associated with doubt. And here, in the case of analysis, it exists around the result of your measurement. And in everyday colloquial parlance, you say it is like give or take. When we see somebody asks for the distance, if you're going to a grocery store and you don't know it and you're tired and you say how far it is, somebody says give or take 1 kilometer. So it could be 1.5 or it could be 0.75, depending on that. So this is the doubt that we have. Okay. So what is the definition for measurement of uncertainty? The ISO guide defines this as a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurand. And you will see later, when we calculate and we express the uncertainty, what this means when we say dispersion. It is a number which comes after the plus or minus. And measurement of answers, so it is the number that comes after plus or minus, and it is expressed. Sometimes we mistake the standard deviation for it, but for measurement of uncertainty, we always express it at a confidence level. So this number which comes after plus or minus is the uncertainty. And the uncertainty is always associated with a probability. It is not that it is an absolute value and it is going to fall between that. You can have the probability with a confidence level of either 95%, 95.5% confidence, or with a 99.5% confidence that it is falling within that plus or minus value. And as we go along, you will see when we have these 95% confidence and when it is the 99% confidence. So the interrelationships now, just to summarize, between error, the true value, the measured value, and the uncertainty. So if this blue line here represents the measurand, and you have been given a plus or the minus value of this. So what is given in red is the true value, and plus the uncertainty. You have the measured value. The uncertainty is the C measured value plus U, or C measured value minus U. That means the value that you're reporting lies anywhere between this line and this line. See, the error is the measured value, the difference between the measured value and the true value. So it could either be a positive or it could be a negative. So this is the relationship between the measured value, error, and uncertainty. So error is the difference between the measured value and the true value, and uncertainty is a quantification of the doubt about the measurement result. So again, trying to compare uncertainty and error, it does not express a difference between two values. The measurement of uncertainty does not have a sign. Actually, it is a number. The plus or minus, what is given, is to show you the dispersion. So we express the uncertainty just as a number. It can be used for correcting any measurement result, and it can be regarded as our estimate of the highest probable difference between the measured value and the true value. And generally, it is represented by the capital U, either in written as such or in italics, to denote a generic uncertainty estimate. So now coming to the question, you and I are analysts. So why is uncertainty of measurement important? So in calibration, where the uncertainty of measurement is there, it must be reported on a certificate. So those of you who have looked, and I'm sure all of you have seen the calibration certificates. If not, please look at those calibration certificates and see whether the certificate contains the measurement of uncertainty. It is required when we, need to look at whether the test result is compliant for regulatory compliance, and so that we have a dispersive value and we can make an opinion whether it is within the limits or not. And tolerance, it is important because you need to know the uncertainty before you can decide whether the tolerance is met or not. So you may need to read and understand a calibration certificate or a written specification for a test or measurement. I mean, if you know what is uncertainty, what is combined uncertainty, standard uncertainty, etc., then it becomes absolutely easy for you to understand any test report or any test certificate or any calibration certificate, and you can always ask the person for the data that is missing in the certificates. So who needs the measurements of uncertainties? The customer needs it to understand the result and to make correct or informed decisions. The laboratory, you and me, we need to know whether our measurement, we have some quality control and quality assurance of our analysis that we are doing. And being regulatory laboratories, it is extremely important that our analyses are perfect. And why should the laboratory report a measurement of uncertainty? The customer, as I said, needs to make correct decisions. And especially when he or she is trying to assess whether the result they have got is within the regulatory compliance and thing. And if you look at our regulations, we either say should not exceed, not more than, or we say not less than, or we give a range. You know, it has to, like for moisture of atta, has to fall between 14 and 16%. So therefore, this is very important. And of course, most important is that all laboratories who are going in for ISO IEC 17025 certification, you should have carried out the measurement of uncertainty for all the quantitative tests in your scope of analysis, you know, that you put into your scope in India for the NABL accreditation. So if you look at clause 7.6, it says evaluation of measurement of uncertainty. This the old clause was 5.4.6 in ISO 17000:2005. And it very clearly says a laboratory performing testing shall evaluate measurement of uncertainty, where the test method precludes rigorous evaluation of measurement uncertainty, and estimation shall be made based on an understanding of the theoretical principles or practical experience of the performance of the method. So therefore, for you, it is extremely important. So now let's come to uncertainty. And as I have previously said, it has any measurement, whether it be a quantitative measurement in physics, chemistry, biology, the bioanalytical experiments in biology, not the animal experiments. They are associated with a measurement of uncertainty, and it is not an exact value. You do not get an exact value. There is no absolute value. And every calculated result has an uncertainty related to the uncertainty in the measured data. And this uncertainty should be reported either as an explicit value after the plus minus, or as an implicit uncertainty. So the numerical value after the plus minus tells you the range, gives you the uncertainty, and the plus and minus gives you the dispersion of the uncertainty. So how do you express uncertainty of a measurement? For example, I am taking the measurement of this pencil by, say, probably using the vernier calipers. And so when I report the results of this after I have taken several measurements of the same pencil, the reported value would be given as 5.65 plus or minus 0.05 centimeters. And you see it is put within parentheses, so that this centimeter is for both the 5.65 as well as for the 0.05. And it is given at the level of confidence at which you are reporting. And that is either at 95% or at the 99.5%. I keep, sometimes I put 95, but generally it is the coverage factor we use is 2 is for 95.5%. So this statement, when you look at it, it indicates that you are 90% sure that the length of the pencil lies between 5.60 centimeters and 5.70 centimeters. Okay, so how is the measurement of uncertainty obtained? The measurement of uncertainty is obtained by statistical methods and other information that we have collected from the sources, from the different sources, by identifying the sources of uncertainty and then putting them all together into a single value. And as you will see, when I say putting together, I will be using the word as combined uncertainty. So combined uncertainty is putting all the uncertainties together. It is the basis for an estimation of uncertainty is the basis is the existing knowledge. You don't need to do research or a thing. The existing knowledge which you get from certificates or thing, and the analysis that you carried out thing. And the experimental data that you want to use generally for this is to use the quality control charts or the validation or interlaboratory comparisons or analyzing the certified reference materials or analyzing any sample that has come into your laboratory, analyzing it 10 to 15 times or asking two analysts to do the analysis 10 to 15 times. So data needs to be collected. So before I go into the actual procedure of the thing, let me just describe what are the basic concepts and the tools that are used in the measurement of uncertainty. One is the normal distribution. Two is the mean, the standard deviation, and the standard uncertainty. Number three is the standard deviation of the mean. Four is A and B type uncertainty estimates. And number five is rectangular and triangular distribution, because we use these terms throughout in the calculation of the measurement of uncertainty. So what is this normal distribution? This normal distribution is a curve which is actually comes from plotting the quantity y or any measurement for you against the probability of it falling within that curve. And this curve is derived from this equation, fy is equal to 1 by s into this to the negative power of y minus ym. In this equation, fy is the probability, and so you see it is on the y-axis, and ym is the mean value of the population. Here, when we talk about population, we mean what you analyze in the lab. It could be the lead concentration, it could be the moisture or anything. In statistics, we refer to this as the population. S is the standard deviation of it, and ym is the mean of the population or the mean of your analysis. So the y-axis and the s characterizes the width of the curve, that is the normal distribution of the curve. And here you will see this normal distribution is something that in statistics we talk about as a Gaussian distribution, where the distribution on either side of the mean is exactly similar or that. So this is a normal distribution that is commonly used in the measurement of uncertainty, and it is related to the standard deviation, as you see S. And in any analysis, we always calculate a standard deviation and a mean. So therefore, the distribution is, correlated to the standard deviation as well as the mean. So how it relates to the standard deviation, if you look at the curve, the standard deviation and the mean are the two parameters, as I said, which determine the shape of this curve, and the standard uncertainty, which is, for us, defining the standard uncertainty, which is denoted by the lowercase u. So what does this curve say? This curve says for any of the analysis or the analytical results to fall between plus or minus 1 standard deviation is to the extent of only 68.3%. If your value is the probability of your value falling between the two standard deviations, that means either minus 2s or plus 2s, is about 95%, 95.5%. The probability is 95.5%. And the probability that it fall between three standard deviations is 99.7%. And in our calculations for the measurement of uncertainty and food analysis, most often we use the standard, the confidence levels or the probability of the results falling between the two standard deviations is 95.5%. That means we're 95.5% sure that whatever value we are reporting is between two standard deviations. 68.2 between one, the 68% confidence is too low, and the 99.7% is, when you are really looking at extreme, you want it absolutely perfect. For example, in GMO analysis, our testing requirements, we always do the analysis to get a 99.7% confidence. So the mathematical terms that you need to know and understand how to calculate are the arithmetic mean, the standard deviation of the mean, and the relative standard deviation. Of course, in our times, all these formulas we had to know, and it still remains in our minds. But now the calculator is available, or the Excel sheets are available, which easily do these calculations for you. And, you can just put these values into that. Yet, I think you need to know the basis and know these calculations, and then you will start appreciating what you are doing when you're calculating the measurement of uncertainty. So basic statistics are required. And in analysis, everyone says, how many measurements should I make in, for an ordinary analysis before reporting? And in my opinion, you should do 3 replicates. I mean, when we come to measurement of uncertainty, I will tell you we need to do 10 or 15, but for reporting results, you need to do at least 3, because if you do 1, the chances are that it may be correct, it may be wrong. If you do 2 as duplicate and the 2 vary, by things, so how are you sure that 1 is correct or 2 is correct? However, if you do 3, at least among the 3, 2 of them will be close to each other, and your values are little, and you could report them. If all the 3 are different, then you are a bad analyst and you need to repeat it. So the statistics for that, so even your analysis, when you are calculating standard deviations, you need to have a minimum of 3 results. But when we come to uncertainty calculations, we need to do a minimum of 10 to 15 replicates of the same sample. So the arithmetic mean is, it gives you as the mean says, it gives you the average. And for getting better results, you need to make more replicate measurements. Say, for example, we are doing a pipetting, and we do the pipetting n times, then the arithmetic mean of this Vm is equal to V1 plus V2 till Vn divided by the number of times you have pipetted. And so this is the formula for it. The arithmetic mean, what it denotes over here is, when you calculate it from an infinite set of values, is the more results you use, the closer you will get to an ideal estimate. And of course, making more analysis or making more replicates is an extra effort, and it is cost, it's cost prohibitive, but the yields are diminishing returns. So what is a good number for an arithmetic mean? 10 is a popular choice because it is very easy to do the division, when you take the average of it. I mean, this is not a written rule. It's not the rule of thumb. But as I said, for ease of thing, it is there. But you can do as many as you want. And the more you do, you will see that your arithmetic mean, the mean that you get, and the standard deviation is much lower. Then we have the standard deviation, which is a scatter of the value obtained from the repeated measurements. And so here in this example about the pipetted volumes, so it tells you the difference for each pipetting. So if I have V1, the difference of V1 with the mean divided by n minus 1, and we square this, and you get the standard deviation. this number n minus 1 in the denominator is known as the degrees of freedom. So as the degrees of freedom increases, you will find that the standard deviation will decrease. And the degrees of freedom will change with the number of replicates that you have done, because n is in the denominator. And as you increase, from 10 to 15 to 20, you will see that the standard deviation will think. So therefore, standard deviation, it is better to have it from at least 10 to 15 replicates, especially when you are doing the measurement of uncertainty. So how many readings? As I said, 10 to 15, and the more readings you get, the better estimate you have. Of course, you don't need to remember this. If in the Excel sheets that you use, you can just type in is equal to STDEV and put the number A1 is to A10 or A1 is to A15, and it has calculated for you and gives you the value to several decimal places. So it's very simple. Everything has been simplified. So two important interpretations of the standard deviation. If the mean and the standard deviations are very large, sufficiently has been found from a sufficiently large number of measurements, you will find that the probability that every next measurement will fall within the range of plus or minus 1 standard deviation, and that is roughly 68.4. If we make a number of repeated measurements under the same conditions, and the obtained value characterizes the uncertainty, and this uncertainty, value that we get from the standard deviation is known as the repeatability standard uncertainty. So the repeatability standard uncertainty is what you do as an analyst. Analyst A does 10 to 15, and you calculate the standard deviation, and that is known as the repeatability standard deviation. Now, if the same analysis is carried out by analysis A, B, C, then that is known as the intralab repeatability within the thing. But if the same sample is done by ABC in lab A and then done in another group of that, the standard deviation that you get from it is the reproducibility standard uncertainty. And you can use either the reproducible standard uncertainty or the repeatability, especially when we want to develop a method and to see that the method is working across the thing. And this repeatability, we call this as the non-ideal repeatability, and it is one of the uncertainty sources that we use in all our calculations. Because human error, everyone makes errors, and this is a random error. So therefore, the calculating the uncertainty from the repeatability of the experiments is one of the sources of uncertainty in any measurement. And let me just give you an example of a very common error is, for example, if you're looking at the meniscus of a burette or of a measuring cylinder, unless you keep that in line with your eye and take the reading, you tend to make parallax errors. Either you read lower or you read higher. So this is a human error, and when you get the standard deviation from repeatability, this error can be, we're taking into account this error. So the standard uncertainty is the standard deviation is the basis for defining the standard uncertainty, and the standard uncertainty is denoted by small u. Standard deviation is denoted by small s. So what you do is you calculate the standard deviation from a number of values which are normally distributed, and then you divide the standard deviation that you have got by square root of the number that you are using. So the uncertainty sources that are systematic in any measurement, and which will not change even by doing the experiment 20, 30 times, will get expressed in this standard uncertainty that we think. So the uncertainty, standard uncertainty estimate is very important. And I advise you in the laboratories, you know, when you're doing these repeatability or anything, even if it is a moisture content and for reporting it, so you repeat it at least 15 times, you know, minimum 10 times, 10 to 15 times, and then calculate the thing. So from the standard uncertainty, which is now, as I said, the standard deviation divided by square root of n, there is something which you will also come across known as relative standard uncertainty. So when we are calculating the uncertainty of the a measurement of uncertainty, you will see that in many analyses we use different, we use a volume in milliliters, we have to weigh the sample, which is in grams, and you need to do a titration again, which is in milliliters, and you might be incubating it in an oven also at degrees centigrade. So these are all in different units of measurement. And so when we put them in a formula, you cannot use them in a formula, and the unit you get would be very, very different and complicated. And so therefore, to make it a single unit, we have this relative standard uncertainty. So what is the relative standard uncertainty? Is the uncertainty divided by the analyte or that. For example, if we're talking about the uncertainty, relative uncertainty of the pipette that we were using, and thing, if we divide it by the mean of the value that you get, you will see we have milliliters in the numerator and milliliters in the denominator, and they will cancel. And so we have a unitless number, which is the relative standard uncertainty. So in the calculations that you're doing in food analysis, and from my experience, for most of our analysis, we calculate the relative standard uncertainty. Now coming to the uncertainties and how do you calculate these uncertainties, there are two types of uncertainties, and they are known as the type A uncertainties and the type B uncertainties. So the type A uncertainty we use when we are relating to, we have done a lot of analysis, repeated readings, and by statistical methods, we are getting it. Then we use the type A evaluation. The type B evaluation or the type B uncertainties that are used are from estimates which we get either from the certificates, from the calibration certificates, or we get it from the manufacturers' inserts that they put the specification, for example, the purity of the chemical on the bottle. And we have to use these which are reported by a third party for the calculation of our measurement of uncertainty. And those are known as the type B uncertainties or type B evaluations. And so it is very tempting to think that, we can associate the type A uncertainties with the random errors and the type B uncertainties with the systematic errors, because they are generally associated with the equipment or the chemical that we are getting. So, and then you have very often we use the standard deviation of the mean for this, and this is also for what we use as the standard uncertainty. And this is carrying out, having the standard deviation of n number of, here we have put V because I'm giving you the example of pipetting. You pipette, say you're doing 10 pipettings for an estimation, and this is done by square root. So when do you want to use this standard deviation of the mean, or what we call as this, standard deviation? So we use this whenever this result that we are reporting is used in further calculations. The standard deviation of the individual result has to be used. Okay. And whenever the mean value is used in further calculations, the standard deviation of the mean has to be used. Now coming to the distribution, that is the shape of the errors. This I have gone through is, this is the normal Gaussian or the S-type of distribution. And we use in the uncertainty calculation something called rectangular distribution and triangular distribution. So in a uniform rectangular distribution, when the measurements are evenly spread on either side, and the lowest, between the highest and the lowest, as shown in this upper diagram, this is called a rectangular or a uniform distribution. The best example to give you is on a rainy day, after it has rained. If you look at the raindrops on an electrical wire, which is there, you will see, or a telephone wire, you will see that the drops are evenly distributed on the thing. So this is what the rectangular distribution is. And we generally use the rectangular distribution when we are taking the information from a certificate. So usually it is from a certificate of analysis or the calibration certificate, which gives the uncertainty associated with it, but it does not specify the confidence level. So wherever the confidence level is specified, we need not take the distribution, but wherever it is just given as a plus minus value, say the purity of a chemical is given as 99.6 plus or minus 0.1% purity, then we use the rectangular concentration. So if the concentration of the calibration standard, as said, it says 1000 plus or minus 2 milligrams, we use the rectangular distribution in our calculation. Then you have the triangular distribution and rectangular calculation. What I have told, will tell you earlier, is the value divided by √3. And that is the formula. It will be coming later on. I forgot to put it here. And then we have a triangular distribution. And the triangular distribution is used when the distribution is such that the mean value just occurs either on the left or the right. So this is used, the triangular distribution is used when the manufacturer has not given the error, but has given a tolerance limit. So when a tolerance limit has been given, the nominal value most probable is that, it falls within that triangle. And we will use the, to calculate the standard uncertainty, we use the half width by square root of 6. So uncertainty will be calculated by the value given divided by √6. So you have, for regular and normal distribution, we will do the standard deviation divided by √n. Here, for the rectangular, you do the value given by √3, and for triangular, it is the value given by √6. So those of you who are doing uncertainty, you need to remember these. In the uncertainty measurements, so what are these uncertainties, that because is it random or it's systematic, and whether we use triangular or thing. So it is the random, as I said, is as you keep repeating it, the errors are at random. You're not sure what the error is, because maybe you pipette 0.01 ml more, or when you're weighing the sample, instead of the third digit, you have weighed only to the second digit. And if you're expected to weigh to the fourth digit, and you have done your balance is for the third digit, then you get this random error. But then you can always check yourself. You can always correct yourself and then go to the correct balance. Or, if you have used an uncalibrated balance. The systematic error or the, systematic effects are when the same influence affects the results, day in and day out, because it is something that you cannot do. And so generally, if we say for the systematic effects and errors, we use the rectangular or the triangular distribution. So random errors, to tell you, what are these random errors? They're always present, unpredictable. They could be operators, change in experimental conditions, could be the room temperature has changed because the instrument is giving different results because the temperature has gone up. And if you will see in case of LCMS, MS and GCMS, MS or thing, if you report to the manufacturers that something has happened with the resolution auto, the first thing they tell you is you have not kept the AC on, the temperature has gone above 20 degrees Celsius, and we need 20 degrees Celsius to keep the quarter poles working. So these are things, and then what we do is we try to rectify this, and we try to keep the air conditioner running 24/7, maintaining the temperature 19 to 19. So these are the random errors, and you will see we can always change. There is a possibility for rectifying random errors. Now coming to the systematic errors, as I said, they're typically present, and you will see the distribution of the systematic error. It will not affect the average, but it does affect the a final result of it. And for an example of the systematic error is like a balance. It is always giving you a reading of, say, 0.1 gram less than what it is because of some problem with it. Or if you look at your muffle furnace, you have set it at 525 and it is actually reading 500 degrees. I think somebody needs to mute themselves. Yeah. So again, so especially setting the temperatures of the ovens, etc., and if they do not read exactly what you're expecting to read, for example, the flow rate of a pump, if you have set it at 2 milliliters and it is actually giving you only 1.8 milliliters, that is a systematic error. Until you have recognized it, all your analysis, you will have error. So therefore, how to minimize them is to do careful calibration and use the best possible techniques. So the interrelationships between random and systematic errors or effects and the A and the B types of uncertainty. So you'll see random errors. The usual way of estimating uncertainties caused by a thing is to use the type A. And type B estimation of the uncertainty caused by random defects is generally not there. But if the data or the information on the effect is to be used for other sources, then we use type B. And the systematic error, the usual way of estimating the uncertainties caused by systematic errors is to use the type B estimation. Okay, so here is a thing to tell you how the interrelationships between the random and the systematic effects affects the uncertainty. So here, if you see, if the random effects are very strong, as divided by, the values vary from person to person and thing, as well as if the systematic effects, there's something wrong with the equipment, you will find that the uncertainty is very high when you do the calculation. If on the other hand, your random effects are still very high, but you have reduced the systematic effects, the uncertainty is medium. If the random effects, if all the analysts are getting similar values, yet if the systematic effects, if the balance is giving a wrong reading or the oven is giving a lower temperature, your uncertainty is still medium. So the best is to have that your random effects have to be minimal as well as your systematic effects have to be minimal. Then you will find that the uncertainty is very, very low. And when you do a measurement of uncertainty, also you will find that it is low and acceptable. So what is not a measurement or a calculation? Mistakes made by operators are not measurement uncertainties. Mistakes in the sense is, if they're not switched on and things like that. But of course, the errors will come in the repeatability. Tolerances are not uncertainties. They are acceptance limits which are chosen. Specifications which we give for the equipment are not uncertainties. It tells you only what you can expect from the product. And accuracy is not the same as uncertainty. Because if you look at analysis, we define accuracy, precision, etc. So therefore, we need to use these words carefully and correctively. Okay. Okay. So another two terms in uncertainty, what we do is, especially when we are calculating the standard uncertainty, we calculate this uncertainty of repeatability or the uncertainty of reproducibility when we are trying to see the if the method is working across labs. So reproducibility is the tests obtained by the same method on an identical test item in the same laboratory by the same operator by the same equipment within a short interval of time. So those results, 10 to 15 results you get, is the average of that is known as the repeatability. Reproducibility, on the other hand, are tests which are obtained with the same method on identical test items. It could be in different laboratories, or it could be in the same laboratory by different operators, and it could be in the same laboratory if you have two different equipment, or it could be in different laboratories with different operators and different equipment. So this is the difference between repeatability and reproducibility. Okay. So where do all these errors of uncertainty come, and which we will be now putting together? One is the measuring instrument. One, it might be aging, may not be calibrated. It might not be on a vibration-free bench, etc. And it might be affected by the relative humidity. The other comes from the item that is being measured. If the sample is not stable, if the temperature has gone up and the moisture has gone, or, it has deteriorated. So uncertainties can come from the sample. The measurement process itself, we can get uncertainties that, if you're measuring the weight and it varies. You can get imported uncertainties. This is not our import regulations. However, it is the calibration of your instrument. So the uncertainties associated with the calibration will be, carried along. Operator skill, sampling issues, which actually we are not relating to this, but when we do, because sampling actually contributes to about 70% of the error, whereas analysis only contributes to. So the sampling protocol, which is developed to pick up a sample for it to be representative of the lot, is extremely important. Of course, the environment, the temperature, the atmospheric pressure, the humidity are all these. And this is the reason that NABL, always says that the temperature and the relative humidity has to be maintained and recorded. Because, for example, if your CRM is to be stored at 20 plus or minus 5 degrees, so your room temperature should not have exceeded 25. If on your everyday chart you have 27 or 30 degrees, it will be a non-compliance because you're supposed to store it at 20 plus or minus, whereas your temperature of the room has gone to 27. So therefore, there will be some uncertainty if you use that CRM or if you use that particular primary standard for your analysis. So maintaining the conditions and things is extremely important. So now just to summarize this, the interrelationships between the different types of errors and the performance characteristics. So in errors, you can have systematic or random, and both contribute to the total error. The bias, which contributes, and the standard deviation contributes to the measurement of uncertainty. I'm not going to talk about bias because in the calculations that we use, we are not going to be using the bias. And accuracy, the trueness and the precision, that is the repeatability and the reproducibility, are important. And you will see that the precision is correlated with the random error, and from the standard deviation you measure this. This particular figure has been taken from the journal Accreditation Quality Assurance, and the journal explains it extremely well. So what are the approaches now that, what I would suggest and what all of you are doing for the assessment or doing the measurement of assessment is what is known as the single validation approach. This is what most of the laboratories are doing their measurement of uncertainty calculations on. We have another approach which is known as the GUM approach, the GUM, which is a modeling based and a bit difficult to understand. But for food analysis, the single laboratory validation approach is accepted. And it is also known as the NOD test approach. And the single lab validation approach does not go deeply into the measurement procedure, but it quantifies all the uncertainties, taking them individually, and actually it takes them as batches. Like, we talk about the uncertainty of repeatability, the uncertainty of the balance, the uncertainty of the pipette, the uncertainty of the chemicals, the purity of the reference material, etc. And this is the reason actually validation, this has been given as a validation approach because this is what we use in thing. And it is also known as the top-down approach. So if any of the NABL auditors ask you which method or which approach did you do the measurement of uncertainty, you should be able to tell them that we are using the single lab validation approach, also known as the top-down approach. Okay, so okay, this and in this approach, actually, as I said, we need to take into account the within the lab reproducibility, and that is, as we have seen in the previous figure, it is the precision component which tells us about this. The bias component we are not using because this takes into account the systematic effects that are causing the long-term bias, and because we are using the collective effects of all the uncertainties, it is sometimes not necessary to take the bias, and to make it simpler, we do not use the bias. So what are the main steps and how do you get to the? The first is you need to understand and you need to specify the measurement. So you would put a title that this is the measurement of uncertainty for moisture of wheat flour, or for the detection of weevilled grains, etc. The second step is to identify all the sources of the uncertainty which could affect your analysis report. So, it could be, if you're talking about the moisture, it could be you're weighing it. So it could be the balance, it could be the temperature of the oven, the operator who is doing it. So you list out all the uncertainties which could possibly affect your thing. Then you simplify each one of them and group them into either the type A uncertainty or the type B uncertainty. Then using the formula that I have showed you earlier, what you do is you calculate the arithmetic mean, you calculate the standard deviation, you calculate the standard uncertainty, because that is a type A. If you are using equipment like the pipette, the burette, the volumetric flask, the balance, the oven, water bath, etc., you look at the calibration certificates and see whether you have got the calibration, the uncertainty is given, or if the tolerance is given, so that you can calculate the type, the other uncertainties. Then you see if the chemicals are there, if purity is given on the bottle or with the leaflets that are thing. So this second step is actually extremely important, because you are gathering information so that you can calculate the measurement of uncertainty. And I'm sure all of you are familiar with the fishbone diagram, which I will be showing you, which puts together this thing. So after we have done that and we have calculated and the standard uncertainties, the type B and type A, we convert them into relative standard uncertainty. And from the relative standard uncertainty, we make what is known as the combined uncertainty, which is known as the sum of the square root of the sum of the squares. And from the combined uncertainty, we multiply it by the coverage factor, depending on whether we want to express as 95.5 or 99.5. And in the examples that I'm going to show you, we use 95.5. And then you give the value with the measurement of uncertainty. So the whole procedure of doing the measurement of uncertainty and the documentation, I will be actually going through with you. So as I said, in step one, what you need to do is standard uncertainty, and you need all the contributing uncertainties and calculate the standard uncertainty for each one. And that, as I said, will be represented by you, as you will see. Then you see whether the standard uncertainty is a type A or it is a type B. And if it is a type A, the standard uncertainty is equal to the standard deviation by the square root of 10. And so n is the number of measurements that you have made. So the standard uncertainty of the mean has historically also been called as the standard deviation of the mean, or the standard error of the mean. So this is very important, and actually this is one of the only calculations or experimentations the laboratory has to do for the measurement of uncertainty, because everything else you will be taking from certificates or calibration certificates or purity data which is given on the chemical bottles. Okay, so this is just to recollect that we use a normal distribution when we are expressing it. And this normal distribution we have seen is only possible when you have done several analysis and you're getting the standard deviation. So as we say that we are going to express it as 99.5, that 95.5, so that means the value that we give is going to be dispersed across either -2 standard deviation or -1 standard deviation. Okay, then you calculate the standard uncertainties of the type B estimates, which are there in what you have listed. And you can do this from the certificates or the tolerance limits which are given. And this rectangular, for rectangular distribution, you give a by root 3, where a is the semi-range between the upper and the lower limits, or it is the value given plus or minus. And you can these are the imported could be imported from the calibration certificates or the purity certificates that are given. And this rectangular distribution, this is to tell you that the specification limits of where you want to use the rectangular is, like for examples, in a pipette it is given as 25 milliliters plus or minus 0.05 ml. But in the glassware and thing, it is extremely important to see at what temperature this tolerance limit holds good. And if we are operating at a temperature different from what is given on the glassware, we need to make corrections. And I'm going to show you how we do that. And then here is an example of doing the calculation of a type B estimate from a calibration certificate. For examples, a specification of the balance. If you look at the balance, the manufacturer says that the reading is within plus minus 0.2 milligrams with 95% confidence. From standard tables of percentage points on the normal distribution, a 95% confidence is calculated, and we can use this figure. If the limits plus minus a are given without a confidence level, then there is reason to expect that we need to use a by 3. So if the confidence level of 95.5 is given, we know that in the case of 95.5, you will see we use a coverage factor of 2. And so therefore, we can just divide this plus minus 0.2 by 2, and you will get the value of 0.1 when the coverage factor, because when it is given with 95% confidence, that means they have used the coverage factor for the calculation. When no such confidence is given, we use a by root 3. Okay, so triangular distribution, this is, we use it when the values are close to x or very close, that near the bounds of it. And here, for example, if in the case of a 10 ml volumetric flask, which is certified to plus or minus 2, but the in-house checks which you do are rare, but you have calculated the standard uncertainty as that. And then, as I said, when we do the uncertainty calculations or anything, when we do for a pipette, it is in milliliters. When we do for temperature, it is in degrees centigrade. When you're expressing moisture, it is, percent. And these are all in different units of measurement. And so therefore, to bring them into the same units, because we cannot compare, apples with pears, we need to compare apples with apples or pears with pears. And so then what we do is we, as I said, we calculate the relative standard uncertainty by, dividing by the actual volume or the actual mass that we have taken, and we get what is the relative standard uncertainty. And these we use for the combined uncertainty. Okay, so when do we use just the standard uncertainty, and when do we use this relative standard uncertainty? Actually, some of the rules of the thumb are, if you are using, doing the uncertainty measurements for some compounds and things which you measure at very, very low levels, at levels like in terms of ppm or ppb, then we need to use the absolute uncertainty, means the standard uncertainty. If we are using it at medium and higher concentrations, then we can use the relative uncertainties. So if you have seen in many cases, especially when we do the acid value or thing, we get uncertainties of 0.39 plus or minus 0.39 if we are using this. So we can use the absolute uncertainty there. And in general, we can use the standard uncertainty where, it doesn't make any difference in the then once you have calculated all the standard uncertainties, identified and calculated all the standard uncertainties, you need to calculate what is known as the combined standard uncertainty given by the letter UC or UCY. And the combined standard uncertainty you calculate, you collectively put all the type A, type B uncertainties, and you use what is known as the summation or the root of some squares. So the combined standard uncertainty will be given by uncertainty 1 squared plus uncertainty 2 squared till all the certainties. Or, if you have the same to the power of half is nothing but square root. And this is extremely simple in the Excel sheets if you can do it. This is known as the root sum of the squares, and this is what we use for the combined uncertainty. And in the Excel sheet, if you do it, you can just type in is equal to square root sum SQ, and you can put whichever cell numbers that you want, whether it is A1 or B1 or C1 or so. So the computer or your laptop actually calculates this. Although we can use, either subtraction or summation in this, most often we use only the sum of the root squares for it. Okay, and then to express the uncertainty, we need to multiply the combined uncertainty with the coverage factor. These coverage factors are given based on whether you're using 68.3% confidence or 95.5 or 99.3. As I said, commonly we are using the 95.5% coverage factor, which is 2, to make it simple. And the value we get is the expanded uncertainty, or the uncertainty that we are actually reporting, which is usually given by the symbol of capital U, and it could be in italics. So this is K into UC, and K is the number. And as I said, generally you would use 2 and say that you're reporting it at 95.5. So this is the coverage factor. And, this is just to reiterate that if you're using a formula such as this, what we use probably in, moisture, or we are using in terms of concentration or thing, then you would use that combined uncertainty. And, the combined uncertainty as given, as I showed you, is the sum of the squares of the relative uncertainty, relative standard uncertainties, which you can see. And here the combined uncertainty is divided by the measurement value. And so when you are expressing this, it will go to the right-hand side. And as I said, there is no rule of the thumb to use it, but you can use it for high and medium concentrations. But at the low concentrations, avoid using this relative standard uncertainty. Okay. Because this is the same, I think it got repeated. I'm sorry. So the coverage factors are given here. These are statistical factors. And so if you want to express at any other level other than what I have told you, this is what you do. So if you want to give exactly at 95%, you multiply by small k is 1.96. If you want to express at 99%, you multiply by 2.56. So these are for the confidence level, the coverage factors, and how you express the result. Okay, so now how is this, how is the result expressed? And as I said, we all know that it is an expanded uncertainty. which is equal to K by the combined uncertainty, and generally we are using the. So if we see this example and you are given this word that the measurement of uncertainty 7 expanded uncertainty U with the coverage factor of KU corresponding to the 95% is estimated. So what it says is, if we give it as total nitrogen, as you see, it is given within parentheses and percent. So it can be, the value can be between 3.66 to 3. Well, minus 8 is 4 and 3.38. So the reported uncertainty, as I said, when you report it, you have to give it with you have to express what coverage factor you have used. So the measurement of uncertainty also, from all that we have seen, as I said, it takes into account the bias, some part of the bias, but we are not including everything in, and we do not use the results. And you can see this is, the values from two different labs, where the uncertainty here, this lab calculates the uncertainty based on the standard deviation plus or minus 1, that is a 68.3, whereas when they have reported it at the higher thing of 95% confidence, you see the difference in their inter-laboratory comparisons. All right. So the uncertainty in the analytical result may be taken into account when you are assessing compliance, and all of you are regulatory officials and you have to give your opinion. So you need to understand how to do this. So if the result is plus uncertainty thing above the limit, or is the result above limit but is within the uncertainty limit, or is the result below the limit but the limit is within the uncertainty, and if the result is minus uncertainty. So you have to look at the uncertainty and do the plus or minus calculations and then give your opinion. Although in our form B right now we do not have a tabular column to express the uncertainty, but it would be wise for you when you're reporting or giving your opinion that you are basing it on the measurement of uncertainty, if you are basing it on the uncertainty. So now let's just get down to the basics. So what we do is we specify the measurement process, then we identify all the sources of thing, to summarize all the sources of the uncertainty, then we quantify that uncertainty, we characterize it, we convert those uncertainties into a standard uncertainty, then we calculate the combined uncertainty, and then we multiply it by 2 to get the expanded uncertainty. Okay, right. So for type A calculations, if you want to do it, we will be doing it. So you take the values, you calculate the arithmetic mean or the average, then you calculate the standard deviation, and then you calculate the standard uncertainty, which is SD by square root n. Now, when you come to doing the type B uncertainties or anything, for example, if you're taking the electronic balance and you have the certificate of analysis from the certificate, your calibration certificate, and the calibration certificate has given the value for the specific weights at 95% confidence level, then you can divide, if it is at 95, you can divide that value by 1.96 to get the standard uncertainty, because they have given you the combined uncertainty. Similarly, if they have given you for balance accuracy and they have not given you this 95% confidence level and given it as 0.2, then we assume the rectangular one and we can calculate the balance accuracy by 0.0012 divided by root 3. If for the resolution factor they have given the accuracy is 0.1. Then again, assuming the rectangular one, we can do 0.1 divided by square root of the, and then we can calculate the uncertainty of the balance as, which is the square root of ub1 squared divided by ub2 plus ub2 squared plus ub3. So this gives you the uncertainty of the balance. And in the balance, we need not make any other correction for temperature or for relative humidity or heat of expansion. However, when you come to volumetric pipettes, for example, if this is a volumetric pipette and it is given, this is a glass pipette, and we know that glass can either expand or contract due to heat, so we need to make corrections. So these corrections are made if the calibration certificate gives you, as I said, the confidence level. So then you just divide it by 2 and you get it. However, if you're given only the tolerance, which is plus or minus, or the readability, and here we apply the triangular distribution, and so we will divide the tolerance by square root of 6. And then we need to make corrections for the coefficient of expansion. And the formula for coefficient of expansion is to multiply the temperature difference by 2.1 into 10 to the power of minus 4. That is actually 0.0021. So, you know, if the, as I said, in either your pipette or your standard flask, it says plus or minus 0.01 milliliters at 20 degrees. However, your temperature is 27, then you need to multiply by 7. So 5 is the difference in temperature, and multiplied by the coefficient of expansion, and then divided by square root of 6. So these corrections have to be made, especially for glass. So you will make these corrections for a pipette, for a burette, and for a volumetric flask. This is again a repetition of the balance, and I'm going to, you know, allow you to, I will send a PDF file of this, so this will be available with you. So the common parameters in our analytical techniques that we would look at are mass, volume, formula weight, purity of the reference materials, you know, and the water bath. I forgot to put the temperature. All right. So this is again the measurement of uncertainty for a balance from the manufacturer's specifications. So if the accuracy of the balance from the manufacturer certificate is given as 0.002 grams, the resolution is given as 0.001, and the uncertainty of calibration is 0.006, then we can use this, you know, as I said, this is rectangular. So divide this by root 3, divide this by root 3, divide this by 2, and then do some squares of all this. And the final uncertainty for the balance is this. So this is an example for a volumetric pipette, and this is a 5 ml pipette. If the calibration accuracy or the tolerance limit as is given as 0.015, it's triangular. So divide by square root of 6. The repeatability, this if you have pipetted it out several times, so the standard deviation by 6. The temperature variation, if you are using the pipette at a different temperature, as I said, that difference in the temperature multiplied by 2.1 into 10 to the power of minus 4 by square root of 3, and then do the sum squares. And here the temperature variation for water, the coefficient of expansion is plus or minus 3, and it is for the glass is 2.1 into 10 to the power of minus 4 per degree. So you look at the difference for the temperature, and you make the corrections. So this we will skip. Now coming to how do you calculate the uncertainty associated with the purity of a chemical. So for example, if the purity of a chemical is given as 99.9 plus or minus 0.1, you can use the rectangular one, and so you can do 0.1 divided by root 3. If a range is given, like 99.9 minimum, 100 max, we know it is, between plus or minus. And here, because the range is given, we can use a triangular, and we would say 0.1 divided by root 6. If on the bottle the purity is given as 99.9 plus or minus 0.1 at 95% confidence level, then we know this 0.1 is the combined uncertainty. We use the normal distribution, and so we would just divide this by 2 and we would get 0.5. So you have to see how the purity is given. And when we look at the purity, purity is given in case of acids. If you look at the purity of hydrochloric acid, it will be given as 35%. That is because hydrochloric acid only exists as 35 grams per 100 gram. So we need to look for the purity rather than the concentration. So as I said, concentration for hydrochloric acid is 35%, but the purity will be given differently. So do not assume, because there are some acids which cannot give you 100% value. Like hydrogen peroxide, you cannot get anything higher than 30%. Hydrochloric acid is 35%. Nitric acid is 64%. So you need to know the difference between the concentration of the acid and the purity of the acid, because several manufacturers give you the concentration. Okay. So this is, a correction for, say you have pipetted the thing, and this is how you would express it. Any value for volume, as I said, the measurement of uncertainty would be expressed like this. So V is equal to 10.000 plus or minus 0.038 within parentheses. Milliliter is that, and K is the coverage factor. Please remember that when you give the value for the measurement of uncertainty, this value that you give and the measurement of value must have the same number of decimal points. You cannot have 10.10 here and give 0.038. If you are giving 10.0, you need 00, you need to give it as 0.04. So it is extremely important that the number of decimals that you give in them at the end of them, when you're expressing the measurement of uncertainty, must be there, and we must give the coverage factor and the confidence level. So the parenthesis bracket means unit ml is valid for both the value and the uncertainty. Norm means the output quantity is expected to be approximately normal distributed. Then this together with the coverage factor 2 means that the presented uncertainty is expected to correspond to approximately 95% coverage. And so to help you, as you have this for saponification number, I thought, just let me put this before I go to the Excel sheet. So if you look and all of you recollect how you do saponification number, we define saponification number as the milliequivalents of potassium hydroxide required to do that. So what is the method and what is the equipment and where will the uncertainties come from? So the major sources of the measurement of uncertainty, if we identify, come from how you weigh the sample. So the mass of the sample. So what you do is here you need to put the mass of the sample. That means the uncertainty is coming from the balance. Then the uncertainty can come from the molarity or the concentration of the hydrochloric acid that you are using for titration. So where does the uncertainty come for the hydrochloric acid? you will be making, you dilute, say, the 11.6 normal hydrochloric acid, you will dilute it to get 0.1 normal. So then you do a titration with a primary standard to get the exact concentration of the hydrochloric acid. And that primary standard that you are using is sodium carbonate. So your analysis or your molarity of hydrochloric acid depends on the correct molecular weight of sodium carbonate, the purity of the sodium carbonate that you use, and the volume of the sodium carbonate that you have used for the titration. Then the next is the titrant. Yeah, that is the potassium hydroxide that you are going to get. So you need to do that. And so the volumes, so you'll be using a pipette, you will be using a burette, and you don't use a volumetric flask, you just use that. So the errors can come in from the pipette and the burette that you use. So you need to do the repeatability of the experiment, and you need to do the for the pipette and the burette, you will use the rectangular distribution for any changes in the temperature of the room that you are doing your titration in versus the temperature of the pipette. So this is what is known as the fishbone diagram, where you try to analyze and put into place all the uncertainties that you would have to take care of for calculating the measurement of uncertainty. So the next step is, we have seen it is, one of the uncertainties, as we have characterized, is coming from the balance. And so, as said earlier, we can get the linearity, and we can get the readability, or even the with the coverage factor. So we calculate the uncertainty of the balance by this formula, which you should be familiar with by now. So the next uncertainty that has come is the uncertainty with the volumetric pipette and the burette. So if we are looking at the volumetric operation, so you do this for the burette. So for the burette, you do the uncertainty of the calibration, what I showed you. Then you make the corrections for the temperature, and this depends on the tolerance, and we can calculate the uncertainty which we are going to experience from the burette and from the pipette. Okay. Next, let's come to the sodium carbonate, which we are using as a primary standard here for this. And if there is no data given on the bottle on the purity or the measurement of uncertainty, we can assume the rectangular distribution because it is over a wide range, and plus minus value is not given. So you can put 100 minus purity divided by 2 into root 3. Then what is the uncertainty associated with the repeatability? The saponification, the titration can be carried out by the analyst at least 10 or 15 times, and you can calculate that. Then you calculate the combined and expanded uncertainty. They combine the uncertainties and then do the expanded uncertainty. So this is to tell you how you would go about the okay. This actually tells you how you're going to do the uncertainty. So I would like to go into using the Excel sheets, but if there are questions on this before I go into we have about half an hour or a little more, I can go through examples of exactly how to do it for some of the analysis, and it might be helpful to you. But if there are any burning questions that you want to ask me, please go ahead now, in case you feel you might forget. Okay. So there are no questions. So if I do not go through the Excel sheets, will you be able to do the uncertainty in a systematic manner? Yes, Amber Ghosh, go ahead. You can unmute yourself and ask the question. Mr. Ghosh, please go ahead and ask the question.
Mr. Ghosh, if you could please unmute and ask your question.
I am not.
I suppose there's some connectivity.
Okay. Yeah. I don't find any other hands up or thing. So Amber Ghosh, relation between decision rule and thing. Yeah. See, your decision rule is exactly what I told you in that, a figure I gave, where I've given the bars and I've given 4 decisions. So let me give you an example. If you have, if our regulation says that the acid value should not be more than 0.8, say, milliequivalents of potassium hydroxide or so, and your measurement, you have got a value of 0.9, or you've got 0.9, and your measurement of uncertainty is 0.15, then 0.9, even though it might be higher than 0.8, because the measurement of uncertainty is 0.15, that means the value lies between 0.75 and a little higher, and 0.75 is less than 0.8, and so therefore your decision would be that it meets the specification. You cannot say it is non-compliant. So what you have to do is, when you have put a measurement of uncertainty, you have to see the distribution. So you do the minus and the plus. So you will get 2 values and see whether those values, the regulatory compliance falls within that. Then it is compliant. If the value is outside, that distribution, then your decision is that it is non-compliant. Hope you understood. All right.
Mr. Ghosh, any other questions from anybody?
Okay. There is another question. Is it possible? Can the describe again how we will decide the uncertain for a particular normal, rectangular, and triangular? Okay, so that thing I can explain it again. Normal is generally if it is based on what do you call an error that you can correct. If it is a human error, repeatability. Generally, we will use the normal distribution for repeatability, reproducibility, and things like that. The triangular and the rectangular are given when, for example, in the triangular, you use, just say a tolerance limit is given. So the tolerance limit is given plus or minus 0.1. Okay, so that means the the purity is triangular. It lies between 2. So then we use the triangular, when the tolerance limit or something is given between plus or minus. We use the rectangular when nothing is given and it can fall, anywhere. And generally, if we are taking it from the calibration certificate or from the manufacturer's instructions, we would use the rectangular distribution. Yes, there is a process for microbiology, but for paucity of time, I did not do this. Actually, it's a little bit different where two analysts, do 15 samples each. And, there is a procedure for the measurement of uncertainty for microbiology. I thought because, the chemical itself is such a big subject, I did not touch upon the microbiology. But microbiology does have, and the procedures are generally based on the repeatability, and two microbiologists have to do it, and they have to do it at two different concentrations and get it. Yeah. Let me see. There is which method? Ma'am, could you please share the method specification? I don't understand. Which method? Sharmista.
Sharmista, could you please elaborate on your question?
What do you mean by method? I'm going to now through what do you call Excel sheets show you the method of doing it. Is that what you mean?
Okay, yes, ma'am. Actually, good afternoon, ma'am. This is Sharmishta. Hello,
Okay.
ma'am. Are
Yes.
you am I audible, ma'am?
Yes.
Yes, ma'am. Actually, I was asking you about the specification. Means for microbiology uncertainty measurement, which method I should use? Can you please give me any example or maybe the number?
I can, if you send me the thing, I can tell you. I have the PowerPoints on the microbiology where we do two independent and analysts do it, and how to do the calculation and things
Okay,
like
ma'am.
that.
Okay, ma'am.
Yeah.
Okay, ma'am. Thank you, ma'am. Thank you so much.
I thought I should just, this is such a big one. I thought I should, I think. Okay. How can I, considering including, without including it in the food analyst report, you can give it. You can say that your opinion is based on measurement of uncertainty, or in your form B, when you report, you can put the measurement of uncertainty. But,
okay, ma'am.
Your food safety officers and the designated officers, I think they need to undergo some training on understanding, they may not need to know what is MU calculation, but how to interpret the data when the food analyst has sent it to them. You can always add it there. Okay.
Okay, ma'am. Okay, ma'am. Thank you, ma'am. Thank you, ma'am.
Yeah. Okay, so I think I will just start sharing the thing so that I could go through the Excel sheet. Okay, so here is a very simple, is this visible to all, or should I make it bigger?
It's visible clearly.
Okay, so I'm going to think. So this is a very simple calculation that I thought, most of you, and maybe you all will include it in the thing. So this is the, so always when you make an uncertainty document, it must have a title. Of course, you need to put the header, footer of your lab and give this document a number because for traceability reasons. That I haven't put. But it needs to have the title. So you can say uncertainty measurement for discolored grains in whatever. So this is the test that you are doing. So then you put a scope. Okay. So you say the scope is the measurement of seeds with discolored grains and determination of uncertainty measurements under the same conditions of measurement in chana dal. And then you need to describe the procedure of the experiment in steps. So what is it? You mix the contents of the 4 sieves freed from foreign matter. And, actually this is missing. We have to, principle of the method is that we mix the contents of the 4 sieves freed from foreign matter and spread it out evenly. So the steps are that we need to take exactly about 20 grams from different parts by the quartering of the thing. Then with the help of the magnifying glass, you need to pick out the seeds with serious defects by hand and calculate the percentage. So the formula, the way we calculate it, you also need to give the formula for the calculation, where the discolored grains mass by mass is equal to W1 into 100 by W, where W1 is equal to the mass in gram of seeds with discolored grains collected, and W is the mass of the total sample taken for the test gram. So please note here, you're using the balance 2 times. You're using the balance to weigh the initial sample, and you're using the balance to take the mass of the seeds. So when you're doing your uncertainty calculation, the uncertainty will get multiplied 2 times, because for, the calculations we make is for single use of the balance. So you are using the balance 2 times. So be sure when you're doing the calculation for the uncertainties, you multiply it 2 times. Then what are the uncertainties in this particular procedure? The uncertainties is, of course, the human uncertainty, that is the measurement, and 2 is the weighing of the sample, or the uncertainties that come from the balance. Then you write what is the equipment used. So you need to put out the equipment that you have used. You need to put the calibration date, when it was calibrated, etc. So, this is to satisfy ISO 17025. Then, what is the information that you need to know before you take the thing is, you need to know the repeatability and reproducibility of the method. And here, generally, it's only the repeatability that we are using. And you also need to know the linearity, the readability, etc. of the balance. So then you draw a fishbone diagram. Here, it's a very simple fishbone diagram, because the uncertainties are coming from the repeatability, that is the operator's uncertainty, and the other uncertainty from the instruments is coming from the balance. If you want here, you could also add the uncertainty coming from the sieves, because the sieves have to be calibrated so that only a certain particle size goes through and that remains. So it does not 100% contribute to uncertainty, but still the sieves also would, so you could include that. So what are the uncertainties that will come under type A? This is the observations are made under the same conditions, and the type A would be the operator's repeatability test. So here you give the values, and you give the discolored grain and how many times you have done it. So if you have done it 10 times, and then you need to take the mean. So as you see over here, if you put it into the Excel sheet, is very simple. If you learn to use it, and you put is equal to sum of C65 from here till here divided by 10. So you get the mean. Then next you can calculate the standard deviation. So the standard deviation also, you see, is very easy. So you can put the formula is equal to standard deviation C65 is to C74. That means take the standard deviation from rows C65 to C74. So what you get is the standard deviation. Then in the same column, you can use the same column to calculate the standard uncertainty, because here, we know standard uncertainty is equal to the standard deviation by root of n. So if you put that, so here it is C76 is this row, and you put as square root of n. See, when you're using Excel, you should know how to put in the terms and how to put in the formula. So it becomes extremely easy. Then the balance standard uncertainty which is given in the calibration certificate and the coverage factor. The certificate says it is 0.1 milligrams at confidence level of 95% coverage factor. That means K is equal to 1.96. If they had said 95.5, this would be 2. So now the uncertainty which comes from the balance at that coverage factor, you see, is this is 0.001. So we need to actually divide that by the 1.96. Okay, so they have done this divided. If you see this one, it gives E83 divided by E84. So what you get is the balance uncertainty. And since we have used it 2 times, we need to multiply it by 2. Then we put down, we make a table, and we make a table and we put down the type of evaluation, type A, description, repeatability, linearity, what was the value. So the repeatability, the mean was 1.309 and 50 grams was weighed. You know the standard uncertainty because these have come from those rows. And then you calculate the relative standard uncertainty. So here you see E91 by D91. That is this divided by the value and the linearity of the balance divided the thing. And generally, because they are expressed in different units, you saw we need to multiply for the combined uncertainty. We need to multiply by the value. So combined uncertainty is equal to total mean value multiplied by the root sum squares. So you'll see the formula given here. So it is the mean multiplied by the square root of sum square of G91 to J92, which is nothing but the sum square of these two. So you see this is actually J91 and this is J92. So the formula becomes easy. So here you have combined uncertainty. So you see sum square of G91 by J92. Then you get the expanded uncertainty multiplied by 1.96. Over there, thing is given. And then the final result is the mean is 1.309 and expanded is there. Since it is a percentage, there is no thing of giving it to the third decimal. First decimal is sufficient. So you can give it as the mean, 1.3. Although I said we must express it as mean percent, you have to give it as 1.3 plus or minus 2% at a coverage factor of K with a 99.5% coverage norm. So that is how you would express this. So this is a very simple way for just doing for the grains. And then I will now show you a little more complicated, I will share with you a little more complicated calculations for the measurement of uncertainty. No, I think I had opened the same one. Okay, so here I'm going to show you the measurement of how we can do this in the Excel sheet for the measurement of moisture. No, this is the, I wanted to do this for moisture by the the titration method or distillation method, or also known as the Dean and Stark distillation method, which we use for spices. So we have a title, then you have given the scope, which is the measurement of moisture and determination of uncertainty measurement under the same conditions. You write down the measurement procedure, and as can be seen here, this is weigh 20 grams of the powdered sample into a 500 ml Pyrex flask, add enough toluene, approximately 75 ml, to cover the sample completely, connect the Pyrex flask with Bidwell Sterling moisture receiver and Liebig condenser, pour toluene into the moisture receiver, bring it to boil and read the volume of water and calculate the percentage. So these are in brief, the steps which you would which are carried out to do this. So the sources of uncertainty, the measurand here is the moisture in the herbs, spices and thing, and it depends on the weight of the sample, the post distillation, and the volume that is corrected. So the formula is very, very simple. The moisture is equal to 100 into the milliliters of moisture collected divided by the weight of the sample taken. So the equipment used is a Mettler Toledo weighing balance, Bidwell Sterling moisture receiver, and they have not written that we are using a pipette to measure the volume. The raw material is nothing but the herbs and size. So what is the data to be assimilated? Repeatability of the method validation. That means, the single analyst or maybe two analysts in the lab do it. The linearity of the balance receiver and the Bidwell Sterling moisture receiver, which is calibrated to measure the volume. So if you look at the fishbone diagram, this is very simple because the factors that could include are the weighing scale, the repeatability, and the Bidwell moisture thing. So the quantities of for type A, the observations were made in surrounding temperature, and the sample temperature is maintained at 27.3. So if you see N is equal to 5, so 5 different moisture estimations were done. And I have, you could either put this in, as I said, just to use the formulas here. So the standard deviation is equal to this. So you get the standard deviation. But in this case, this has all been calculated thing. So standard deviation mean by using the large formula, the complete formula. But what I want to bring to your attention is when we use the formulas in Excel, they are exactly the same as if we expand it and we use. So then you come to the uncertainties. So coming to the uncertainty of the balance, the certificate which was given says that it is 1.8 milligrams at a coverage factor of K2. We need to convert this 1.8 milligrams into grams because we are measuring the amount of the herb or the spice in grams. So we say that is equivalent to 0.0018. Since they have said at a confidence level of 95 or 95.5, we can take either 1.96 or 2, and so you get this value. Here the balance is used only once, so therefore it would be taken. Now coming to the moisture receiver, if you look at that, the moisture receiver is a calibrated equipment which has come with a tolerance. So we can assume that it is a triangular distribution. So the tolerance was given as plus or minus 0.05. So you divide that by square root of 6 into 10. You get that. Then the uncertainty due to the temperature of the coefficient of expansion is what is the difference in the temperature given in the calibration in the certificate for the condenser, for the moisture receiver and thing. So as I had explained to you, you see the difference in the temperature multiplied by the coefficient of the expansion of that into the temperature, and then divided by square root of 6. So the uncertainty of the Billings-Stirling moisture receiver, which is similar to thing, is 0.050116. Then you make a table of the type of description and evaluations, whether it is type A or type V, what is the value there of it, and you calculate the standard uncertainty from that, from the values that you have, and then you calculate the relative standard uncertainty is this ux by x, and you get that combined uncertainty is equal to mean of that certainty, and then what you get is that. And since you are, you have to abide by or meet ISO 17025, you need to write prepared by, checked by, etc. The technical manager and the quality manager, and the report or the measurement of uncertainty calculation should have a header and a footer. So let me show you a little more complicated one, which is the titratable acidity, which has more than what I showed you, but very similar. So you talk about what is the scope, how do you do the measurement procedure, the sources of uncertainty, what is the formula that you use for the calculation, what is the equipment that you have used. So here you have the weighing balance, the burette, the pipette, and the volumetric flask. So you need to take each one of these uncertainties individually for the calculation. And so what is the data to be assimilated before the measurement, the repeatability of the method validation, the linearity of the balance, the uncertainty due to the burette, the pipette, and to the volumetric flask. So now you draw a fishbone diagram, and so you see the weighing balance. In the glassware, it is the pipette, the volumetric flask, and the burette. In case of purity of chemicals, here we need to take the purity of sodium hydroxide, and we need to take the purity of the potassium hydrogen phthalate, which is used to standardize the sodium hydroxide. That is the purity of these two. And we need to use the type A1, that is the repeatability of the experiment. So the fishbone diagram sort of helps you to understand, what are all the necessary things to do. And then quantification of the uncertainty measurement of the type. So you have done it, you've done it at room temperature, which is 27.3. So using this thing, this should not be moisture, this should be milliliters of thing. So as I said, you calculate the mean, you calculate the standard deviation, and you also calculate the uncertainty that this is a standard, because this is normal distribution divided by root 10. Then the type B calculations, it will come from the balance. Again, the certificate is given, you're taking it from the certificate of it. If it is not there and you're taking it from manufacturers, you can take linearity, readability, all that into consideration. And here you do this thing. Then you take the volumetric flask, you assume the triangular distribution, the tolerance which is given with this volumetric flask is plus or minus 0.17 ml. So therefore 0.17 divided by square root of 60 into 500, which is the volumetric flask. So you have this value. Then you make the uncertainty corrections for the coefficient of expansion. Your working temperature is 23, whereas the calibration is given for 22. So the difference in temperature is 1 degree. So 1 degree into 2.1 into 10 to the power of 4. Now assuming triangular distribution for the difference in the working temperature, this divided by the 23 into by the square root. So now you have the uncertainty of the pipette. Similarly, you calculate for the burette, which is 50 ml plus or minus 0.05. So put in the same values, and for the coefficient of expansion, because the temperature you have used, this is calibrated at 20 degrees and we are having a value of 3. So the difference in temperature is 3. And then for the pipette, the same thing. You do the tolerance. It's a triangular distribution. So calculate this. Now let's come to the sodium hydroxide. So if you look at the sodium hydroxide, the purity is quoted on the supplier's catalog that it is within the limits of 99.90 plus or minus 2%. Okay, so when we say plus or minus 2%, we have to think. So that means the purity, if we want to reduce it into thing, is 0.9990 plus or minus 0.02. So this is the uncertainty. So I would divide this, this is rectangular. So this is the uncertainty you get. Similarly, for the potassium hydrogen phthalate, it is there. So you calculate the for the potassium hydrogen phthalate, if the molar mass of the sodium hydroxide given on the bottle is, if from the atomic weights and the quoted uncertainty, many companies give this, especially for the primary standards. You calculate the standard uncertainty for that, and then you put all the uncertainties together. The molar mass of potassium hydrogen phthalate, because it's a primary standard, the difference from the atomic weight, the uncertainties are given. So we calculate the standard uncertainty, and then finally what we do is we put together all the uncertainties to do the combined. So repeatability, purity of sodium hydroxide, purity of potassium hydrogen phthalate, mass of sodium hydroxide taken, mass of potassium hydrogen phthalate taken, the molar mass, the uncertainties due to that, the uncertainties due to the volume of the volumetric flask, of the titrant that you have used, and the linearity of the burette, of the pipette, and the volumetric flask, and you put all these together, and then finally you do a combined uncertainty, which is given there. These need to be changed because it should be sodium hydroxide and potassium hydrogen phthalate. So these are and then you calculate the value and the uncertainty. So these are a few examples of the uncertainty, how you could do the uncertainty calculations. Yeah. So now, yes, you are asking a question. Is it necessary to take in consideration the purity of sodium hydroxide and potassium hydrogen phthalate? Yes, because the sodium hydroxide, if you are standardizing with potassium hydrogen phthalate, you don't need to take that, but you would have to take the purity of the potassium hydrogen phthalate into account.